So this is the lecture on chapter 2.2, Ionic solids in our course of solid state physics. So what we will do here is that we will go through the concepts that explain to us how ionic solids are being formed. So mainly here we will rediscover a Madelung constant. I believe you have already discovered that in the earlier courses. And we will mention what are ionization energies, electron affinity, cohesive energy, and these concepts that then allow us to understand how strong bonds are being formed in ionic solids. So this is what we will be covering, and I will first start with the kind of general motivation of the process, how ionic solids are being formed. So when we have an ionically bonded system, the electrons, they seem to be completely transferred from the electropositive atoms to the electronegative atoms. And when that happens, that an electron really is being displaced from another atom to another one, there will be a Coulombic attraction then between the formed ions. And this is of course a simplification. The assumption that we have ionic bonds, the real truth is a little bit more complicated, but at least this is a good picture. So we really imagine that the electron is really gone into another atom, and then two ions are being formed. And then because of these two ions, we have electrostatic attraction, and that gives rise to a formation of solid. And then we will look next into the details of this process, and we learn that the Madelung constant is a very, very key parameter here that describes how strong ionic solids are being formed. So this is the kind of key ingredient when we are looking into ionic bonding. And graphically, what happens is that we start with two charged neutral atoms, so that they have equal amount of protons and equal amount of electrons, so that they are charged neutral. And then one electron hops from the electropositive atom to the electronegative atom, and subsequently what happens is that then we will have two atoms or ions, so this actually is the better word, and the other one is electropositive, the one from which the electron moved to the electronegative atom, the blue minus sign sphere here, and then there will be Coulombic forces, electrostatic forces that then put these two ions together. And when we have many of these, an ionic solid will be formed. So this is graphically what happens in solid formation when ionic solids are being formed. So for example, sodium chloride is a good example of that, or cesium chloride and other similar salt compounds. And now we go and rediscover what's a Madelung constant, and then we learn how do we calculate that. But this is of course covered already in the structure of matter course that we have in our university, so this may not be a very, very big surprise to you of this what will be going through. So in ionically bonded systems, the electrons are transferred from the electropositive to the electronegative. So this is what happens, and Coulombic attraction is being formed. And what we do next is that we estimate these binding energies for a case of two atoms. For example, a sodium chloride, it's a good example molecule. And the ionization energy of a sodium ion is 5.1 electron volt. Electron affinity of chloride ion is 3.6 electron volts. And then how much it takes energy for creating a sodium chloride molecule is 5.1 minus 3.6 electron volts. So 1.5 electron volts. And this is a molecule, not a solid. So the energy gain due to the Coulombic attraction, we can calculate that. Like that's a simple piece of math. We have minus E squared. So we have plus charge and minus charge, and divided by 4 pi vacuum permittivity epsilon naught times A, where A is the distance between the ions. So A is around 2.8 angstroms, if I'm getting the unit right. So this results in a energy of 5.1 electron volts and this energy gain. So basically what it means that this calculation, that in total, like we lose energy 1.5 electron volts, but we gain 5.1, so that it's energetically favorable to form a sodium chloride molecule. And that's why sodium and chloride will form molecules. And since we're interested in solid pieces of matter, what we want to do next is that we want to generalize, we want to repeat these procedure for a crystal and not a single molecule, and this is what we will do next. And details are left as a homework. Please recap what you have already discovered in your earlier courses. And the total energy gain for a crystal, we can calculate that the gain will be minus 1.748 times E squared divided by 4 pi epsilon naught times A. And this value, 1.748, that's known as the Madelung constant. And that you will be calculating as a homework assignment. So what you do is that you take into account the fact that now you actually have a sodium chloride crystal, and then you need to calculate what's the electrostatic attraction and repulsion between the different ions in this solid crystal. And please note that if we have Madelung constant that is greater than unity, what that implies physically is that the solid can actually be formed, so that energetically it's more favorable to form a solid than not a molecule. But if Madelung constant would be smaller than unity, like energetically it would not be favorable to form a solid, and then you would actually have a powder form of your substance. And since we do know that many of the ions actually are not like atomic molecular powders, but they're actually like a little bit larger crystals. For example, the sugar and salt, we know from kind of like a kitchen chemistry that it's not like molecular powder, but it's actually like a far coarser grains, so that we know already that the Madelung constant must be greater than unity in lots of the substances, salts, and different compounds. And please remember that Madelung constant only is a good concept when we are dealing with ionic solids. So ionic bonding can be understood simply by considering the energy balance and minimization of energy when we are forming a solid. And in order to help us out, these below terms have been used and defined. So there's a thing known as a cohesive energy, and please be warned that there are different ways to define what's a cohesive energy, and our book and booklet are using a same way, but the other people may have a different meaning for a cohesive energy. For us, in this course, it is the total energy difference between the solid and the isolated constituent atoms. So in essence, like mathematically put or chemically put, we want to describe a process that we have two atoms, A and B, and when we put them together into a substance AB, like the kind of energy need that we need for this process to take place, that's called cohesive energy. Ionization energy is another energy, and that's the cost for turning an electropositive atoms into ions. So equation-wise, that's the cost when we take a substance A, atom A, and we turn that into an electropositive ion, A+. And similarly, electron affinity, but please note for the sign change in the energy, cost, it's the cost for turning electronegative atoms into ions. So from B substance into B ion, so B minus. And then the lattice energy is the final term to cover here, and that's the total electrostatic energy gain when we form the crystal from its isolated ions. So in practice, when we have atoms A in ionic form, so we have A+, and when we have B-, and when those form a substance, the amount of energy we need or we kind of get is known as the lattice energy. So in terms of the terms we have defined here, the lattice energy E lattice equals to the E minus ion minus the ionization energy minus the electron affinity minus the cohesive energy. That's the way to calculate the lattice energy. In practice, calculation of this lattice energy E lattice is often tricky, and in practice we need to know the real experimental interatomic distance A. As you recall that in the Madelung constant calculation, we do have the interatomic distance, and if we do not know that, then we're bluntly put screwed, because we cannot finish the electrostatic calculation. So that also motivates nicely why X-ray diffraction and structural characterization methods are important, because sometimes when we do calculations, we actually do need these kind of experimental values for the lattice constants. So either way, either we need experiments or we need quantum mechanics, and there we would need to take into account the Pauli and repulsion processes. So these are the things that matter when we are forming ionic solids, and we are now done in this chapter, and next time we will return and we will speak about covalent bonding and covalent solids. So thanks for listening, and hopefully this was a nice piece of lecture for you. Thanks and bye-bye.